Hi friends, welcome to my YouTube channel. This is first part of lecture number 22, and in this lecture we will study circuit and waveforms of one-phase half-wave controlled rectifier with RL load having freewheeling diode. So this is the circuit diagram of rectifier. Here we can see that load is RL type and we get output voltage V0 across this load. This freewheeling diode is connected in parallel with this load, and this whole combination is connected in series with this thyristor, and this whole circuit is supplied with source voltage Vs, where Vs is equals to Vm sin omega t, and this is the waveform of source voltage Vs. Now this rectifier circuit operates in two modes. First is discontinuous conduction mode, second is continuous conduction mode. First we will see the discontinuous conduction mode. During this mode we get I0 up to beta, or output current we get up to beta due to this inductor L, and this beta is assumed between pi and 2 pi plus alpha. Okay, so we will study discontinuous conduction mode in three angular slots. First we will study the operation from 0 to alpha, then from alpha to pi, and then from pi to 2 pi plus alpha. So first we will see the operation from 0 to alpha. From 0 to alpha, positive cycle of this sinusoidal waveform is applied to this thyristor. When positive cycle is applied, then positive potential reach the anode of this thyristor. So this thyristor get forward bias, or we can say that VAK is greater than 0. But gate pulse is not applied yet, or we can say that thyristor is not triggered yet. That's why this thyristor goes into forward blocking state and act as open circuit. Now this negative potential reach the anode of this diode. When this negative potential reach the anode of diode, this diode, that is freewheeling diode, get reverse bias and it act as open circuit. So this thyristor is in forward blocking mode and act as open circuit, and this freewheeling diode also act as open circuit. Here it is equals to 0. So freewheeling diode current is equals to 0 because it is open circuit. Here it is equals to 0 because we are talking about discontinuous conduction mode where beta is between pi to 2 pi minus alpha. So that's why we get freewheeling diode current that is equals to 0. Now when this thyristor is open circuit, then we get source current Is is equals to 0. Here suppose this is current Is, source current Is. So Is is equals to 0 because thyristor is open circuit. Okay. So now what is drop across thyristor? When this thyristor is open circuited, then the source voltage Vs will appear across this thyristor. That's why drop across thyristor is equals to source voltage Vs. Or we can say that this portion of source voltage Vs in this waveform will appear across this thyristor. Okay. Now what is output voltage V0? When this thyristor is open circuit and this diode is also open circuit, then we get voltage V0 is equals to 0 because no current flows in this circuit. That's why I0 is also equals to 0. Actually it is shown greater than 0, that is for continuous conduction mode. I will cover continuous conduction mode in my upcoming slide. So for discontinuous conduction mode, I0 is equals to 0 from 0 to alpha. And what is power P0? Here we can see that V0 is equals to 0, I0 is also equals to 0. That's why we get output power P0 also equals to 0. So here we can see that in this waveform V0 is equals to 0, I0 is also equals to 0, and thyristor voltage Vt is equals to Vs. Please ignore this blue waveform because this is for continuous conduction mode. Here you have to focus only on this dotted waveform, that is for discontinuous conduction mode. Okay, here it is up to beta. This is beta. Now what happens from alpha to pi? At omega t is equals to alpha, this thyristor is fired and VAK is already greater than 0 for positive half cycle of sinusoidal wave. So both the conditions to make the SCR turn on are satisfied. First, VAK, that is anode to cathode voltage, is greater than 0 and gate current is applied to the gate terminal of this thyristor. So this thyristor gets turned on and it acts as short circuit in forward conducting mode. So from 0 to alpha, this thyristor gets short circuit. When this thyristor gets short circuit, we get output voltage V0, that is equals to Vs, and that is equals to Vm sin omega t. And due to positive half cycle of sinusoidal waveform, this diode will remain reverse bias. Now what is output current I0? This derivation of current I0 is already been told to you in one phase half wave controlled rectifier with RL load, and in lecture that was on one phase half wave uncontrolled rectifier with RL load. In both these lectures this derivation has already been told to you. But from exam point of view, there is no need to remember this derivation. Only you need to remember that we get output current I0 up to beta. Okay. Now what is drop across thyristor Vt? When this thyristor gets short circuited, then drop across thyristor will be equals to 0, or we can say that Vt is equals to 0. Now what is source current Is? During this period, Is is equals to I0. Because thyristor is short circuited and this freewheeling diode is open circuit. That's why this Is and I0 will be same. Now what is current across freewheeling diode? As freewheeling diode is reverse bias, that's why current across freewheeling diode will be equals to 0. And what is output power P0? Here from alpha to pi, we can clearly see that I0 is greater than 0, V0 is also greater than 0. That's why we get output power P0 greater than 0. Now what happens after pi? It is really important. After pi, the polarity of sinusoidal voltage waveform reverses. So we can represent the polarity of sinusoidal waveform like this. So when polarity reverses, then this negative potential reach the anode of this thyristor and this positive potential reach the anode of this diode. So this thyristor gets reverse bias and this diode gets forward bias and act as short circuit. So when this diode acts as short circuit, then the current I0 which was flowing through this thyristor shifted to this diode. Why it is shifted to diode? Because this current I0 get the minimum resistance path with this short circuited freewheeling diode. That's why when polarity of sinusoidal waveform reverses after pi, then this freewheeling diode get forward bias and act as short circuit, and this current I0 now shifted from this thyristor to this freewheeling diode, and this I0 will freewheels in this loop, or we can say that I0 will flow through this resistance R, this inductance L, and this freewheeling diode. So when this current gets shifted in this loop and VAK is already less than 0 for this thyristor, so the current across thyristor becomes 0, or we can say that source current Is becomes 0. When current across thyristor becomes 0, then this thyristor goes into reverse blocking mode, or we can say that this thyristor get open circuited. Okay. Now we will conclude some important points from this. First is when polarity of sinusoidal voltage waveform reverses, then we get output voltage V0 is equals to 0, because this output voltage V0 is equals to drop across this freewheeling diode, and drop across this freewheeling diode is equals to 0. That's why we get output voltage V0 is equals to 0. Second point is when polarity of sinusoidal voltage waveform reverses, then current gets shifted from this thyristor to this freewheeling diode. That's why the path of this output current changes. When the path of this output current changes, the equation of this output current also changes. So here this output current I naught after pi has different equation. Third point is that the drop across thyristor is equals to source voltage Vs, because when thyristor get open circuited, if we apply KVL in this loop, then we get Vt is equals to Vs. So this negative half cycle will appear across this thyristor. Now here in case of this rectifier circuit where we use this freewheeling diode, we get source current not equals to output current. Okay, this is one more important point. Here we can see that when this freewheeling diode conducts, then source current becomes 0, but I naught is still flowing. That's why we get I naught not equals to Is. Here, due to this freewheeling diode, what happens? Suppose in this circuit, freewheeling diode is not used. Then in that case, we get output voltage V0 like this. Okay, so we get this negative part also. But due to this freewheeling diode, this negative part get eliminated. Because of this elimination of negative part, what happens? The average value of output voltage increases because this net positive area increases, and output power P0 is equals to V0 average into I0 average. If V0 average increases, then output power also increases, or we can say that system efficiency increases. Third point is, we know that power factor is directly proportional to the average output voltage. So if average output voltage increases, then power factor also improves. And next important point is, we know that P0 is equals to V0 average into I0 average. So due to this freewheeling diode, this negative part get eliminated. That's why we get output power P0 always positive. While in case of control rectifier without freewheeling diode, we get negative part of this output voltage, and due to this negative part we get negative power, and this negative power means energy fed back to source, or we can say that energy flowing from source to load to source. So due to this freewheeling diode, when this negative part get eliminated, we get only positive voltage V0. When voltage is always positive, then we get P0 always positive. That's why no power is fed back to source. So all these are advantage. Now come to the continuous conduction mode. Here we can control this beta by controlling the value of R and L. If we make the R and L such that we get beta greater than 2 pi plus alpha, in that case we get continuous conduction mode of this rectifier circuit. So if beta is greater than 2 pi plus alpha, then we get continuous conduction mode. This blue waveform of output current is for continuous conduction mode, and these yellow blocks for current across freewheeling diode are also for continuous conduction mode, and the source current Is is also shown for continuous conduction mode. Here we can see that after pi, when this freewheeling diode start conducting, then whole current shifted to this freewheeling diode, and we get output current across this freewheeling diode. So here in this waveform, this output current flows from pi to 2 pi plus alpha, because this is continuous conduction mode, and due to this we get continuous output current. That's why we will continue to get current from pi to 2 pi plus alpha. After 2 pi plus alpha, this thyristor is again triggered. When this thyristor is triggered, then this thyristor goes into forward conduction mode. When this thyristor goes into forward conduction mode, it acts as short circuit, and this diode is reverse bias. So after 2 pi plus alpha, this output current I0 again shifted from this freewheeling diode to this SCR. So after 2 pi plus alpha, we get output current I0 across SCR, and it is equals to source current IS. So this is the waveform of source current IS, or we can say that it is the waveform of thyristor current. Okay. So after knowing all this, now we can easily understand the operation of discontinuous conduction mode from pi to 2 pi plus alpha. From pi to 2 pi plus alpha, what happens? Thyristor is continue to act as open circuit because it is reverse bias, and current across thyristor is also zero. That's why it acts as open circuit. Here this thyristor acts as open circuit, and what we get output voltage V0? We get output voltage V0 that is equals to 0 due to the short circuited freewheeling diode. And what is output current I0? Here in previous slide I already told you that after pi the equation of output current changes. Now what is new equation? To get the new equation we have to apply KVL in this loop, that is freewheeling loop. So we get I0 R is plus L di0 by dt is equals to 0. On solving this we get I0 is equals to A e to the power minus R t by L. On putting omega t is equals to pi and I0 is equals to I pi naught. Suppose at this point pi the value of output current is I pi naught. So putting this we get A is equals to I pi naught e to the power R pi by omega L. Put this A in this equation of I0, we get I0 is equals to I pi naught e to the power minus R by L t minus pi by omega. But this equation is not important from exam point of view. Okay, now what is drop across thyristor? We know that from pi to 2 pi plus alpha, thyristor acts as open circuit. That's why the source voltage will appear across this thyristor. If you apply KVL in this loop, okay, then you will get Vt is equals to Vs. So the source voltage will appear across this thyristor from pi to 2 pi plus alpha. Now what is source current Is? Here Is will become 0 because this freewheeling diode starts conducting. And what is current across freewheeling diode? It is simply equals to output current I0. Now last is output power P0. Here output power P0 is equals to 0. Why it is equals to 0? Because V0 is equals to 0 after omega t is equals to pi. So this is all about this video. I hope you like the video. Thank you. Jai Shri Ram. If you got the knowledge and concepts from this video, then please like the video and subscribe the channel. You can give your views and ask any questions related to this topic in comment box. Also share this video with your friends because sharing is caring. Don't forget to press the bell icon to get the notification of my upcoming videos. Thank you.